He developed a mathematical, you don't have to write really anything down from here either, mathematical way of determining the wave and particle nature of the electron. And it ended up falling under the umbrella of quantum mechanics. We're going to talk about that electron density graph in just a minute. But this is what you need to write down about Schrödinger and what we use it for. Square of the wave equation. This is psi, Greek symbol psi, gives a probability density map of where an electron has a certain statistical likelihood. Well, basically 90% likelihood, okay? 90% likelihood of where it's going to be. Now, if you're looking here at this graph over to the right, okay, that is like an elapsed time graph of where the electrons have moved and been mapped at, okay? If you look here, okay, low dot density value probability of finding the electron there is pretty low. And the high dot area, so this is the high dot area, okay, that's the likelihood of where you're going to find the electron, okay? And if you look here, it's kind of forming a nice little spherical shape there. And this particular graph is going to be denoting which orbital, which type of orbital. An s orbital. Remember s orbitals? Okay, s orbitals are spherical. So they look like round, you know, spheres around the nucleus, which the nucleus would obviously be, you know, dead center on the map there, okay? So his wave function's a very high level bit of physics here that we're not going to get into, way beyond the scope of this course. Allows us to be able to see these densities and be able to predict where the electrons are going to be 90% of the time. So when you write out an electron configuration and you're putting electrons, when you're putting electrons in, say, like the 2s or the 3p or the 4d or whatever, you're really saying this is where we believe it's going to be 90% of the time. Okay? So that's the purpose here of Schrödinger's equations and wave functions. Okay? No, you don't need to write every little bit down, I promise. Now, we need to talk about orbitals, because this is where the important application level and where your problems are going to be coming from. Okay? The wave equation gives us a set of wave functions or orbitals and their corresponding energies. Orbitals and their energies. Each orbital describes a spatial distribution. So it's like a 3D space. 3D space where that electron's going to be. Okay? The orbital is described by 3 sets of quantum numbers. And yes, we have to go back over quantum numbers, and I know we didn't spend a lot of time on it last year. I know my group got about a day and a half of quantum numbers. So you might recall some of it, you might not. It might be like, oh yeah, I remember what n is, but I don't remember what L is, or m sub L, or m sub s. We're going to go through the quantum numbers again. Okay? But once again, you're not writing everything down. You need to realize what we're doing is the orbital. It's a 3D spatial arrangement of where the electrons are going to be. Okay? And we describe where they are using quantum numbers. Okay? Principle of quantum number n. Everybody knows quantum number n? When we say principal energy level, this we're talking about where the orbital resides. Okay? Principal energy levels, we use what to figure them out? What do you use to figure out the principal energy levels? The what? What? The row, yes, on the periodic table. That's what I was hoping to hear, is periodic table. We use the periodic table, yes. The row you're in on the periodic table, yes, row. Slash period. How many rows or slash periods do we have? 7. 7. So there's 7 principal energy levels. Now remember our periodic table method, the S and P's are equal with their principal energy level rows. The D's and the F's are off a little bit, but we'll talk about that in a minute. So we use our periodic table to denote, so periodic table, this is how we figure out our principal energy levels. Okay? Okay? Yes, that's what we were going for. Thank you. Okay? Now, principal energy level N, you just go with the row that you're in to figure out its particular quantum number. Okay? The angular momentum number, known as L. Okay, this is the L number. The quantum number defines the shape. This is all you need here, is the shape of the orbital. That's all you need to know about L. On the next slide, I want you to write down what's on the next slide. You don't need to write all the rest of this down here. We use the letter designations S, P, D, and F, but their L numbers never change. They're always the same L numbers. You can just memorize it off of that. Okay? So, you wrote down shape of orbital. Let's go over which orbitals go with which number. S-shaped are always going to be zeros. P shapes are always going to be 1 for their L, D shapes are always going to be 2, and F shapes are always going to be 3s for their L's. Okay? So, if I said my electron is located in 4D, my electron's located in 4D, my first 2 quantum numbers, the first one would be a 4, because that's my N number. My second number would be a 2, because my L is a D, right? So N is 4, because that's the principal energy level. L is going to be a 2, because we're in a D shape. Okay? So far, so good. Following the quantum numbers again. Because now we're going to get to the tricky one, M sub L. That one's the hardest one, I think. The magnetic quantum number describes the orientation of the orbital. Orientation of the orbital. Now, what do we mean by orientation of the orbital? Remember, if we had a P, right? A P sublevel, right? Remember those were 3s? D's had how many of them in there? D's had 5, right? Okay. So, the D's are a little bit harder to visualize because their shapes are really funky. But the P's are pretty easy because the first one is the P on the X plane, the second one is the P on the Y plane, and the third one is the P on the Z plane. They have one on each plane at the coordinates there. So, which one are you in? Are you in the X one, the Y one, or the Z one? And this is how you label them when it says like negative L to L. So this would be -1, 0 to 1. So if my electron was in this one, my M sub L number is going to equal 0. If my electron was over here in the PZ and it was pointing down, okay, so this one would be, my M sub L would be 1. I know, it's going to come together all at once in a minute, but anyhow, okay. We'll get to the spin one, the plus half, minus half in just a minute. I know you're already thinking about that, the plus half, minus half ones.
I don't know that.
Okay. So it gives you a nice graph of, if you'd like to look them up in your book, but like I said, we'll come to some examples here in a minute. Let's talk about the shapes, though, before we try to put all the quantum numbers together. S's are always spherical. This is all you really have to write. They're spherical in shape. They just get bigger. As you get further out from the nucleus, they get wider. They get bigger spheres. That's all the difference there. Spherical shaped ones. Okay? Now, that's all you have to write there. Looks like a sphere. Okay? The P's, though, we call them. Before we get to the P's, let's talk about these graphs real quick. They show you these graphs where here is the distance from the nucleus and the probability of finding the electron. Okay, so of course we know that they fill the lowest energy level possible. We'll go back over off-valve principle later on, but likelihood the 4s is going to be the closest to the nucleus because it has the lowest energy. Yes, an electron would fill there first. Then here in this graph, this is showing the 2s, this is showing the 1s, this one's showing the 3s. Now, most of the time, the likelihood of where you're going to find the 2s electrons are further out, a little bit further away from the nucleus. Occasionally, they squeeze in from time to time and get closer and move back out. Once again, this is 90% of the time, though, so it's not perfect. It's not like everybody's in their fit little box all the time. Okay? As you can see on the 3s one, the majority is even further out from the center of the nucleus. It's getting that wider sphere and so forth. Okay? Looking at the P's. This is what the density graphs look like. They have them up and down. But as you can see, the P's look like dumbbell shaped. Okay, or that's what they're called. You have one on the Z-plane. Here's one on the Z-plane. Here's one on the X-plane. And then you have one on the Y-plane. Okay, so you have one on each plane. That's why there's 3 in the sublevel. Okay, 3 different P orbitals, all shaped like dumbbells. Okay, they have the 2 lobes and the node in the middle. Okay. Now, I'm going to skip the videos. If you want to watch them spin, you can look up the PowerPoint. The D's. You don't have to know a shape for the D's because guess what? The D's are starting to look a little funky. They look like 4-leaf clovers, but this one right here is like a donut shaped. Okay? And realizing that these are the 3-dimensional shapes as to where the electrons are going to be. So envision me here, with my 5 lines, right? The 5 lines of the D sublevel, right? When I'm putting something in this box right here, or this line, it's going in that shaped orbital. If I'm putting something in this one, it's going in that shaped orbital. So the third one, of course, that one, the fourth one is that shape, and then the last one is the funny donut shape looking one. Okay, so when you're placing the electrons into their orbitals, that's what you're doing, is you're actually placing them into those 3-dimensional weird looking spaces. Okay? And the D's look kind of funny, so I'm sure you can imagine the F's are even more intricate and have a lot more shape to them. But before we get to them, as you can see, these are the density graphs again. You can see the density graphs, how they kind of make those 4-leaf clover shapes there. Okay? Just another reference to the data showing that, where they are 90% of the time. Now for the F's. As you can see, the F's have 7 orbitals in the sublevel. They are even more intricate in their shapes. These are where the electrons are. They travel around in these little areas, okay? I know, quite a lot of intricate math involved in all of that, like I said, way beyond our scope. But when I'm placing something in like the first orbital of the F, we're placing it in the first orbital right here, this funny donut-shaped looking one, okay? Exercise 5. For principal quantum number n equals 3, determine the number of allowed subshells or levels and the different values of L for each. Okay? So that's a lot of information. In principal energy level 3, what can I have? What are my possible ones I can put things in? I can put it in an S, true. For principal energy level n equals 3, we have a 3s. What else do we have? A 3p, good. We do have a 3d, very good. Do we have a 3f? No, when did the F start? Principal energy level 4 is where the F starts. So in this particular case, we would only have an S, a P, and a D. possible. Okay. Different values of L here. So what would the value of L be for this guy? This is 3 for its N number. What would its L number be? 0, right? This one would be 3, and then it would be a 1, and this one would be a 3, and it would be a 2. Now, if we wanted to denote the particular orbital it was in, we would have another number there, and then if we wanted to determine the spin, we'll have the 4th number there. We'll get to the spin in just a minute. Okay? So L equals 0, 1, and 2 for the S, P, and the D. Subshells are the same thing as sublevels, by the way. If you hear that, sublevel, subshell means the same thing. Okay? Let's look at the next one. Exercise 6. Is it exercise 6? For L equals 2, determine the magnetic quantum numbers, M sub L, and the number of orbitals. What would that be? First of all, if L equals 2, what kind of level are we in? We're in a D. Good. So if L equals 2, we're in a D. So, number of orbitals. What's the possible number of orbitals in a D? How many orbitals does a D have? 5. 5 blanks. 5 boxes, right? So that could be like 3D or 5 lines. Some people draw them with the lines like that. So if you're in L equals 2, you're in a D. A D has 5 boxes or 5 lines, so you're going to have 5 orbitals. But remember, 4 of them were like those cloverleaf shapes, and one had the weird donut-looking thing. Okay? So that would be what she would put there for a question like that. Okay? Your magnetic quantum numbers will range from -2 to 2, so I guess I could have drawn that out there. So if this is my D, -2 starts here, and it goes to 0, and then it goes the opposite direction. So if you put an electron right here, 1 arrow up, this one, say it was a 3D, we would be 3 for our energy level. We would be a 2 for the sublevel D, and then our third one would be a 1 because that's the particular orbital that it's in. So this orbital would denote there. And if I wanted to, I could tack on, because it's spinning in the up direction, it would be +1/2. So if you remembered your spins, it's +1/2, -1/2. If you're spinning downward, so if we were doing an electron from here, say I was doing this one, the one that's pointing down in the first one, my 4 quantum numbers would end up being 3 because of the 3, 2 because of the D, and then -2 because that's the orbital it's in, and then -1/2 because it's spinning downward. So quantum numbers, we'll go over a few more examples with that. We're going to look at the magnetic spin here, the 4th quantum number, in just a moment. Okay? So the electron spin number, M sub S, can be +1/2 or -1/2. Those are your only 2 choices. And this is where Pauli exclusion principle came into play. Pauli exclusion, okay, in a given atom, no 2 electrons can have the same set of 4 quantum numbers. So that really tells us that each orbital can only hold 2. So that's really what we're going for, is that they can only hold 2 electrons, because that last quantum number, if it's +1/2, -1/2, nobody's going to have exactly the same address. Okay, and +1/2, -1/2, it looks like it's spinning upward and downward. It's really spinning like a top, and it's spinning clockwise and counterclockwise. Okay? So, for instance, say we're in a P sublevel, we'll say we're in the 2P. Okay? 2P, I have electrons Okay, let's say I'm 2p5, right? Everybody remember 2p5? Say I have 5 electrons in my 2p, that makes me 1, 2, 3, 4, 5, that makes me fluorine. I'm fluorine. Okay? If I filled up through 2p5, I'm fluorine. Okay? So, but if I wanted to address the quantum numbers, say on this guy right here, what are the 4 quantum numbers for that particular electron? 2 is my N number, right? Because I'm in energy level 2. P is my sublevel. So what number do I assign my L number to be? 1. Okay? Now, this is -1, 0, 1. So my M sub L number is going to be a 0 because I'm in the middle one, right? And last but not least, which direction am I going? M sub S, I'm going downward, so I'm -1/2. So that would be my list of quantum numbers for that particular electron.
Oh my gosh.
Does it make sense now? Coming to you? Coming back? Okay, hopefully coming back to you, yes.
More time. There is a point where
okay. So that's just denoting the 4 different numbers. You have N, then L, then M sub L, then M sub S. They're written in that order, and they do have commas between them, yes. And you'll see them in problems denoted exactly like that. Okay, just so you know. Does everybody see that? Just making sure we're all on the same page. Okay, and once again, you don't really have to write anything down about this real quick. But knowing that the quantum number was, detected by a magnetic field, because spinning in different directions, you're negative, you create a magnetic field. Okay, but I do want you to get this visual aid here, because we see the arrows, we put them up and we put them down in the boxes, so we think spin up, spin down. They're actually spinning clockwise and counterclockwise. Okay, clockwise and counterclockwise. So I wanted you to get that visual representation as to, which direction they're going. Okay, so the spin up is really clockwise, the spin down would be counterclockwise. Okay, and going back to that whole idea that we're only going to be able to have 2 electrons in an orbital. Okay, that's Pauli Exclusion principle, and you have to have them having 4 different quantum numbers. That last quantum number is going to allow us to have the difference. Okay. And now going on to some of the stuff from last year that's a little probably more. Oh, no, we're going to go into the penetration effect first. Which way do they prefer to fill? They prefer to fill the lower energy, right? Lowest energy to highest energy. So that's kind of following off-bow principle, starting at the bottom and working your way up. But we know this is the case. S's will fill before P's, before D's, and before F's. So that is the particular order that they're going to follow when they're filling in their possible energy levels, sublevels, and orbitals. Okay? They can't be calculated exactly. We know this because of uncertainty and all of that good stuff. Okay? They prefer the lowest energy level. That's why they're going to fill S first, because S is going to be closer to the nucleus and have lower energy than the P. That's what we're talking about there, the Y. Okay? Orbital energies. Oh, yes, I do want to show you this one. Hang on a second. All right, pay attention, please.
In a hydrogen atom, all subshells for each N are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
Okay, so if you watched it, you would have seen that hydrogen only has 1 electron. So I'll replay it real quick. Hydrogen only has one
In a
electron.
hydrogen atom, all subshells for each end are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
Okay, so that one looks more like the off-bow diagram that you see, where it kind of looks more like a staircase, or like our mountainside party house that everybody did, the house party. Okay, yes, you remember that? Yes. That is because in hydrogen, there's only one electron. You don't have interactions of the electrons. We know electrons are negative, so they repel other electrons. So keep that in mind, that the energies are equal in hydrogen, but everybody else has more than one electron, so they actually end up varying a little bit in their energies. So generally, the 1s is lower than the 2s than the 2p, but the 2s, say in nitrogen, isn't the same energy as the 2s in titanium. Relatively, yes, the 2s is going to be lower than the 2p, but they're not exactly the same calculated energy for each individual atom. Okay? So keep that in mind. But let's reiterate once again about
In
the
a
orbital
hydrogen
energies.
atom, all subshells for each end are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
Okay, so as you see there, for hydrogen only has one electron, so all of its like 3s, 3p, and its 3d here, all of these, okay, are going to be at the same energy. But because polyelectronic atoms have more than one electron, that is where we get the more of the staircase-looking off-bow diagram, because those electron
In
repulsions
a hydrogen
cause it.
atom, all
Watch one more
subshells for
time.
each end are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
So as you see, it starts getting that staircase more look of the off-bow diagram there. And now we're going to talk about why, this happens, and also a little bit more on the energies of the orbitals. Okay, gotta get back down here to penetration effect. I believe that's where we left off. Did we get that down? The penetration effect has to do with the ability to be closer to the nucleus. So the nucleus pulls closer the 2s electrons rather than the 2p, the electrons found in the 2p orbital. Okay, that pulling it closer to the nucleus creates the lower energy for the electron. Okay, causes an electron in the 2s orbital to be attracted to the nucleus more strongly. Ooh, what's going on there? Okay, let's try this again. There we go, much better. Has it more strongly than the attraction to the 2p electron, and based on that penetration, the 2s electron is going to have the lower energy. Now for off-bow, this is kind of stuff from last year. Really, all you have to write here, it means building up. You're starting with the lowest energy level and you're working your way up. Now remember, off-bow is not a person. Off-bow is a German word for building up. Okay? So you're building up, adding electrons into the orbitals, starting with like the 1s, then you go on to the 2s, then you go on to the 2p based off of their energies. 1s is lower in energy, okay, the lowest actually, and then you work your way up through the table to get to the higher energy orbitals, okay, like the 4s is higher energy than the 6s, and so forth if you're following your periodic table. Okay, so building up, really, building up. Okay, so you start with the lowest energy level, lowest energy orbital, and you work your way up. Okay, that's what you need to do here. You don't need to write all of the extra information here, but that's the basic gist here. So if I'm doing oxygen, oxygen has 8 electrons. And we're talking about a neutral oxygen atom because oxygen's number 8. That means 8 protons, so neutral oxygen's going to have 8 electrons. So 2 of them would go here in the 1s. And if you were doing the orbital diagram, we would fill the orbital diagram with our arrows. Okay, the arrows representing the electrons. The 2s then would have to be completely filled before moving on. So we would put 2 in here, and then in our 2p, which we'll get to Hund's rule in a minute, but we would also fill the last 4 in the 2p. We wouldn't put any in the 3s or the 3p or anything like that, sticking to filling this lower energy level before moving on. So we would put the 4 in here one at a time, and we'll get to why it goes one at a time in a minute. But that would be following Hund's rule. Okay? But you would not fill any of the electrons in the 3s if you have 2s available, because the 2s are lower than the 3s in terms of energy. Okay? Good with that? All right. So Hund's rule. Lowest energy configuration for an atom is one having maximum number of unpaired electrons. Unpaired electrons in the degenerate orbitals. What does degenerate orbitals mean? That means it's a p, d, or f, because it has multiple orbitals in the level. Okay? So a p, d, or f is going to be degenerate, because a p has 3 orbitals. Remember, one's on the x plane, one's on the y plane, one's on the z plane. So because it has 3 orbitals in there, we say it's degenerate. The only ones that don't have the degenerate label is s's, of course, because they only have the 1 orbital in there. So you're going to put 1 at a time first, unpaired. This is the empty seat idea, I remember from last year. Or if you were doing the house party, you got your own love seat first before you had to sit with somebody. If you remember that analogy, okay? Keep that in mind. So if I'm filling, say, 4 electrons in my P here, 1 would go in the first one, 1 would go in the second one, 1 would go in the third one. Before you have to pair up that last one, okay? So make sure that you're following Hund's rule when you're in your P, D, and F orbitals, those sublevels, okay? And yes, that word degenerate you might see as being listed, but just know that that means it's a P, D, or F, because it has more than 1 orbital in the sublevel. Okay? And we already kind of talked about Pauli, so previously, but we can reiterate once again, what is Pauli exclusion principle telling us? How many can go in an orbital?
2.
Only 2 electrons. Why is that? Yes, we have 1 spinning in the clockwise direction, 1 spinning in the counterclockwise direction. But why, his rule really states why that is, because we can't have the same, what? Can't have the same address. Those 4 quantum numbers, not the last quantum number tells you that you're going to have a different address. Okay? They can have the same first 3 quantum numbers, but that last 4th quantum number, the plus a half, minus a half, will allow only for 1 electron to have that one same address. Okay? If you have more than 2 in an orbital, then 2 electrons would have the same address, and you're not following Pauli exclusion principle. So you can only put 2 in, and 1 has to spin clockwise, 1 has to spin counterclockwise, so nobody has the same, all 4 set of quantum numbers, being the same. Okay? Yes?
Why do the electrons spin upwards when they're first put into the orbital? And then why do they spin downwards after it's completed?
I believe the data must show that the clockwise direction is the more preferred direction. So when you're in a degenerate sublevel like P, that they all like to spin clockwise first. And then to minimize electron repulsions, if you have to pair up in an orbital, the other one spins the other direction to minimize those electron repulsions. Okay? Or we wouldn't be doing it that way. It must be based off of the experimental data. All right, so orbital diagrams. You can use boxes or lines. Does everybody remember how to draw orbital diagrams? And I do want to make sure everyone makes the quick distinction of what an electron configuration is and what an orbital diagram is. Electron configuration for oxygen, remember 8 electrons, would be 1s2, 2s2, 2p4. This is an electron configuration, not an orbital diagram. Orbital diagrams are boxes and arrows. Arrows are the electrons, or if you see the ones where sometimes they put them as lines with the labels underneath, like so, if you're going to use arrows on the lines, those are also considered orbital diagrams. So following our off-bow principle, we fill the 1s first. Then we move on to the 2s, filling its energy level completely before moving on to the 2p. And that's where the last 4 go. Now we have to follow Hund's rule. 1 goes in each first before we pair up that last one. Okay? So keep that in mind. Now I believe you guys, is oxide on there to do? Let's take a look. What would you do with oxide?
Add 2 more electrons.
You would add 2 more electrons. That's correct. Because you're gaining 2 electrons, so basically you just add them to your configuration. So that's all you really need to do. Okay? Add them to your configuration. So if I'm doing oxide here, I've gained 2 more. That means my electron configuration should have 2 more in it. So I'm going to completely fill my 2p. 2p6 will be the designation now for oxide. So when we're filling our orbital diagram for oxide, we fill our 1s, fill our 2s, and now we're going to completely fill our 2p. 1, 2, 3, 4, 5, 6. Now, as you can see, the orbital diagram and configuration of oxide looks very similar to which other element? Looks just like neon, right? We say it's isoelectronic with neon. Isoelectronic. That means it has the same configuration. Okay? And it would also have like the same configuration as, say, like fluoride. Because fluoride gains 1, so it would also have a 2p6 going on. Or, say for instance, we were talking about sodium. If sodium loses this 1 electron, guess what? It now looks like neon, and it also is isoelectronic with oxide. Yes?
So in this instance, we're having
In this instant, yes, the degenerate orbitals are still there because the 2p is the degenerate level. Degenerate just means it's a sublevel that has more than 1 orbital in it. So that's what we're talking about there. So P, C's, and F's are called degenerate because they have more than 1 orbital in them. Okay? So, keep in mind here, the whole reason why atoms gain and lose electron is to become what?
More like noble gases.
More like noble gases. Why do we want to mimic and look like the noble gases?
Yeah.
Because they are stable. So the whole point of isoelectronic configuration and why they gain and lose electrons to look like their counterpart noble gas is to become stable. That's why bonding occurs. Okay? So, reiterating those points, basic points from other times. So, there's our correct orbital diagram. Now let's talk about valence electrons. How do we do valence electrons?
We count the highest row.
We count the highest row of what? The highest outer energy level, but specifically in that outer energy level, which ones are we going to be looking at? Which ones are always going to be the outer energy levels possible? Which sublevels? P and
S.
It's going to be your S's and P's. Remember that D's start 1 row behind. Remember 3D comes after 4S, so 4S would be the outer energy level there. Okay? So you're really adding up your S's and P's. I was hoping that you remembered our little strategy from last year where if you're in group 1, how many valence electrons do you have? You're in group 2, you have 2. Okay, yes, yes, remember our tall columns all follow that order. 13 or 3A, this is 3A, 3, and then 14 or 4A has 4, 15 or 5A has 5, and so forth, all the way to 18 or 8A, which they have 8 except for helium. How many does helium have? Remember, helium's an exception. Helium could be above beryllium right here because it only has 2 valence electrons. So, watch that exception on helium. Don't forget that one. Yes?
Direct electron configurations. What is the order of the letters?
The order of the orbitals, it's going to be 1s, then to 2s, 2p, then we go to 3s, and we're going to follow the periodic table. So you don't have to memorize them. You can just follow the rows and the blocks, which we're going to go over in just a minute. Okay? Now, say for instance, let me go ahead and looking here, if we have 8 valence electrons and we have this configuration, the element is going to be neon, right?
Yeah.
So you're looking for the outer energy level. The outer energy level is 2. So you would take the 2 and the 6, and that's how you would get your 8 valence electrons. But for instance here, say I'm doing germanium. P2. Okay, so germanium is going to end up on 4p2. So if I'm looking here to do valence electrons off of this configuration, if you can't remember that germanium's in group 14 or 4a, so it's going to have 4 valence electrons, you can always go to the s and p's. So the outer energy level is the 4. You would take the 2 here and the 2 here, s and p, add it together to get your 4 valence electrons. Okay? And that's why we can follow our column system, is because of this reason. That's where it comes from. Okay? So you can keep that in mind when you're looking at valence electrons there. So now we're going to be looking at which energy level starts the D sublevel?
3.
Which energy level starts the D's? The D's start in energy level 3. Here is your periodic table. D's start in the 3rd energy level. Where do the F's start? Here's 4F. So F's don't start till the 4. D's start with the 3. But if you're following the periodic table, and this diagram, this picture is on the back of your notes packet, by the way, so you have it there to look at. Okay? If you don't remember, the S's and the P's follow the rows and periods, the principal energy levels. So here's, S's and P's follow the rows. But remember, the D's start one behind, so it's n-1 for the D's. n-1. So you would fill 4s first, then 3d. So 4s, 3d. Now what you have to remember about the F's down here, it's n-2, so they start 2 behind. So you would fill 6s first, then you go to the 4f, 14, then you come up here and do 5d. Remember the periodic table's long though, right? Because we have our insert right here. I'm sorry, the insert's right there. So we would technically put those 2 rows in that section and it would be super wide, right? So you would fill 6s first, then 4f, then 5d, then to 6p. Okay? That one is a little, we're going up to a little bit higher level with that. We didn't make you do like into the F's last year, but you got to remember the F's come in here. This is the little insert area. Those rows actually are inserted right here. So 6s, 4f, 5d, 6p. Then it goes 7s, 5f, 6d, 7p. Okay? So keep that in mind. All right, configuration for zinc. Zinc is one of the transition metals, so now we've got to talk about transition metals. because they're a little bit special, because a lot of them are moms. What does moms mean again? Multiple oxidation metals. And so they have some little idiosyncrasies to them as well that make them a little different. And some of them don't obey the off-bow principle. They like to fudge on that. So, electron configuration for zinc. Write it out. Let's go. So what is your configuration? Yes, it lands on 3D10 over here. If you 3D10 is going to be zinc. Okay? Now, if I am going to write out my configuration for zinc 2+, remember, zinc is not a mom. Zinc, silver, cadmium, not moms. Remember, they're the different ones.
Yeah.
Zinc goes to +2, silver goes to +1, and cadmium goes to +2. Now, where would we take out these 2 electrons? Where do they get removed from?
Valence.
They do get removed from the valence. They have to come from the outer energy. So when you're removing electrons, you go to the outer one. So we're going to take out our electrons from the 4s. Okay, don't remove them from the D. The D is not considered the outer energy level, even though its energy is just slightly higher than the 4s. However, so when you're writing out your electron configuration for zinc 2+, zinc ion, it would look like that. Also, if you wanted to do the valence electrons off of zinc, regular ground, neutral zinc, you would look here because it's the outer energy level. So this guy has 2 valence electrons. And most of your transition metals will have 2 valence electrons because they fill the S's and then they stop in the D's. Okay? However, there's a few exceptions to the off-bow principle, so we're going to talk about that after we do the noble gas configurations. Okay? So, are we good with this? One other thing to note about transition metals and their colors, because the transition metals are the ones that give us lots of pretty colors. Does everybody understand why that is? They do jump around. Why do they get to jump around in those Ds? Because they have lots of space in the D orbitals to jump around. So they make little jumps, and in those little jumps, they give off energy, and they give off energy in the form of photons. So we see colors based off of those wavelengths, like copper. Copper 2 sulfate, you see those crystals, they're blue, right? That's because the copper, when it goes to +2, it has a space free in its d orbital, and therefore it can jump around a little bit. Some other ones to note would be like cobalts or pinks. Irons usually are a rusty brown color. Nickels are green crystals. A lot of nickels are green crystals. But one other thing to note about, guess what? Zinc goes to 3D10 here. And it loses its 2 electrons out of the 4s. So does it have any free space in its d orbitals? No, because guess what? Zinc is always colorless in its solution. It doesn't produce a color because it has no free space in its d orbitals. Okay? Some of, like silver does the same thing, but we're going to talk about silver in a minute because it's an exception, but its d orbital stays filled, so it is always colorless as well. Yes?
So the color is only determined by the D?
The D, having ability to have electron make minor jumps in the Ds, gives off those wavelengths, and that's why they have a lot of them have pretty colors.
So because S is a lot smaller, that won't affect much, right? Or is it only D then?
Well, it's only D because those are the, having D with 5 orbitals and partially filled orbitals gives you a lot more space to jump around. Your S's are always going to fill, so yes, there's not enough real enough space to make huge adjustments there. You're right. To give off energy in wavelengths and so forth. Mm-hmm. Noble gas configuration. Everybody remember how to do these?
Yeah.
Abbreviated. What do you do?
But for the noble gas before in brackets.
The noble gas in the row above. You got to go to the row above. Okay, and then you start in the row
Afterwards.
afterwards. You're going to start there, the row that the element is in. So let's do cadmium. What's cadmium's noble gas going to be?
Which one is cadmium? CD.
Under zinc. Not along. +2. So we're going to use krypton. We're going to use krypton. Okay, then we start in the row with cadmium. So over here, cadmium is going to start with a 5s2 and a 4d10. So this would be the abbreviated configuration for cadmium. Now, abbreviated configurations aren't all that abbreviated at the top of the chart, but when you get down to some like elements like barium and so forth, okay, then you're going to have some serious, huge, long configurations, so the abbreviated ones help. Okay? So, let's look at some exceptions to the off-bow principle. Some elements are slightly more stable with different arrangements, and it kind of has to do with the half filling or the completely filling of the d orbitals. Or f's, too. This can apply to the f's as well. So, complete half filling or completely filling. So, say for instance, here's a D, and if you completely fill your S over here, okay, but you only have 4 in the D there, what these elements do is they take this electron out of the S, and they half fill that D, and that's slightly more stable for them. Okay, to space it out more. Less electron repulsions, I guess you would, probably why, as to why it would do this. Now, this also works for the completely filling ones. Instead of having 9 in the D, it'll take 1 out of the S and stick it in there and make 10 in the D. And as you'll see in your diagrams below, this usually is going to happen with the copper group and the chromium group. So the elements in those groups typically follow this pattern. So that's going to be chromium, molybdenum, and tungsten, this group. And then we've got copper, silver, gold, that group, okay, that you're going to see this exception rule start to apply. And because silver does this, that's how silver's 3D stays filled, and that's why silver solutions look nice and colorless. Okay? So let's take a look at our examples here. As you see, this one shows you the configuration for copper. So, unstable to leave 2 in the 4s. Instead, it takes 1 out and sticks it in there. So you get this more stable configuration where there's only 1 in the S, but their D is completely filled now. And then for chromium down here, I kind of showed you that. It takes the 1 out of the 4s and sticks it, half filling the D. And that's a more stable configuration for those elements. Okay? Good with that? Now let's do some exercise. Expected configurations for each of the following. Let's go ahead and write those out. Yes, you can use abbreviated because some of them are way, way, way long. Okay, so let's check it out. See if you got these right. I'll do selenium over here for you. Or selenide, because it's actually an ion, so it's selenide. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, or you want to use argon, which is much easier. 4s2, 3d10, 4p6. Okay, how are we doing with those? Doing okay? No. Yes, sir?
I got them right, but for the sublevels, for energy level 6 and 7,
Uh-huh.
how would there be 10, D needs 10 electrons?
Correct, but you would go, you go 6s, then 4f, because it has to go down in those bottom rows, then to 5d. So don't forget that those rows are inserted there, so go 6s, 4f, 5d.
But then 5d would only have
No, because actually on the periodic table over here, these last two are really part of the D.
Oh my gosh. Wow.
So yes, LU and LR are actually D elements.
Wait, so do you count those as D or no?
They are counted as part of D. If you count the rest of that, will if you go from LA to YB, that is 14 elements.
Wow.
Okay.
Okay.
All right, quantum number review. Let's look at quantum numbers real quick before we move on to other bigger, better things. Okay. What are the 4 quantum numbers for the last electron filled in an arsenic atom? So, what you should do is go to arsenic. What is the end part of the configuration for arsenic? End part of arsenic is going to be what? It's going to be 4p what? 4p3, right? That's where arsenic's going to land. So, this is what I always do to figure out quantum numbers. I draw out my 4p, right? Here is my 4p. 1, 2, 3. Which one's my last electron? The last one I filled is the one in the PZ over there. Okay? Now identifying my quantum numbers. Remember, the first in the 4 is the n value, the principal energy level. So what's my principal energy level? 4. So my n value is a 4. Then comes my L. Okay, L is going to be what? What shape is my orbital? It's a P. So what number did they give to the P's? 1. P's are 1s. Remember, S's are 0s, P's are 1s, D's are 2s, F's are 3s.
Yeah.
Now, that's our L number. Next number is M sub L. We have -1, 0, 1. Which orientation, which orbital in the P is it going to be in? It's going to be in the PZ, which is 1. And last but not least, we need the magnetic spin. M sub S. M sub S, are we clockwise or counterclockwise? Clockwise, so it's +1/2. So that would be how I would do my quantum numbers.
Did we get a yeah, boy?
Yeah, boy. There you go. All right. Now, on the bottom set, guys, you need to figure out which one of these are impossible. Out of those quantum numbers, some of them are not possible. Which one's not possible? Try to figure out why, too. Looking at A, is A possible?
Yeah.
Yes, right? Because this would be 1, S, and S only has the one orbital 0. So, yes, that one's possible. +1/2, you can have one spinning in the 1s in the clockwise direction. How about B? Is B okay?
No.
Why is B not okay? So this would be
On the second orbital.
2 and then what? D. 2D. Is that possible? No. So this one does not work. Okay? How about 3?
No.
So 3, this means it's a P. What does that mean?
It has 3.
It means it should go from -3 to 3 in the sublevel. That's really going to be a what? This would be an F, so that one doesn't work. We know that sublevel or energy level 3 doesn't have an F. How about this last one? Does it work? So this is 2P. Does the P have a -1 in it? Oh, yes, it does. And can you have, yep, so that one works. This one works, and A works, but the B and C are incorrect quantum numbers. Okay? So as you see, they can ask multiple choice questions like that as well.